Here
Okay.
RF means forward resistance or ripple factor, sir.
Obviously, it's indicating the forward resistance. Okay. Of the
Okay.
diode. Okay. So that is about the Rafi
I want
rectifier.
to ask a question.
Can you ask
Sir,
the question?
PI is
Okay.
the input power.
Hmm.
Yes, am I right?
PI is the input power, right? Hmm.
So sir, why we have not used the IRMS of that AC source we giving? Because we are taking the RMS value of the current of half
You
wave
can use
rectified.
that, no problem. You can use the AC source IRMS, VRMS into IRMS. That will also give you a PI, not an issue at all. VRMS into IRMS, that will also give you PI. Okay, got my point. But the point what I'm trying to enforce, because we are trying to show the factor eta, how we are getting into this expression. Just to understand that idea, we are getting into this kind of an idea to understand what is the average power. So average power, if I get into that idea, we can do VRMS into IRMS, or as being shown on your screen, which fetches you the idea that is I square into R. That is IRMS whole square, RF plus RL ultimately.
Sir,
So
RF
in
is
this formula, IRMS equals to I by root 2 or I by 2.
I square
I'm
I by
asking
2.
this.
This is half wave rectifier. Let me show once again. Maybe that
Sir,
is getting.
Yes,
sir,
sir.
Look
can you
here.
Then why we
Just
have not
once
used
show
the
this.
explain
IRMS
the
value of AC
from
source?
where sir IDC
Because
comes and
that
what
is
is
the
its
input power.
significance?
First is Im by 2 is giving you the RMS value of the load current, as you can check on your screen. And IDC is the DC value of the load current. That is, you're averaging the load current
Average.
over there. That is
I
this
am by
one,
pi.
Im by pi. You are getting the DC value of the load current in one case, and IRMS is the root mean square value of the load current. And that load current is the current according to the circuit design which is flowing through the diode also. It is the same load current flowing through the diode. So whatever current is flowing through the diode, the same current is flowing through load resistance. Same I RMS value over there. So
Sir,
in
can
that
you please
sense,
explain the definition of ripple factor, sir? I understood the calculation part.
okay,
Definition.
if definition is what is the ripple factor is what? Ripple factor gives you the idea about what is the amount of the variation. What is the amount of variation or comparable amount of variation of the AC output with respect to DC? That is the main thing all about. So to I
Sir,
mean
can you
to
slow sir?
quantify that.
Can you speak
I,
some slowly, sir? I'm not getting.
okay, what we talk about from the what we are trying to get into through ripple factor is this, that when we are having this gamma, the ripple factor, what is this ripple factor? Ripple factor is effectively as being, let me just write it once again. I ripple RMS divided by IDC. I ripple RMS divided by IDC. That is your ripple factor, gamma. So what does it really mean? It means that is whatever is the pure AC component for the outcome, at the outcome, that is the load current, whatever is the pure AC component, what is the root mean square value of the pure AC component? And that value, when it is compared with respect to the DC level of the load current, that is the ripple factor. That is the ratio of the RMS value of the ripple part, that is the pure AC part, to the DC part of the load current. That is ripple factor. And form factor is the RMS value flowing into the circuit. In other words, it indicates the RMS value of the instantaneous component. Obviously, that is what it should be, to the DC component. So that is the form factor. So I hope you
Sir,
understand the difference between the ripple factor and the form factor.
sir, if ripple factor is high, then its AC component is high, means not that much
Very
current in converted to DC.
if the ripple factor component is high, it means that is the AC part. The AC part in the output waveform is pretty high. If the ripple factor is high, it means the AC part in the output waveform is high over there, because you're comparing it with the DC segment. With respect to DC, what is the variation? What amount of ratio is there? If that factor is high, it means the AC parts RMS is definitely high, or in other words, the AC's existence is far more higher at the output, or the pulsating nature is too much in the outcome. The pulsating nature is too much in the outcome. That is what it means through ripple factor, if the ripple factor value is high. So our main intention should be to reduce the ripple factor. And to reduce the ripple factor, the only thing that we can get through is full wave rectification. And that is only possible if we rectify both the half cycles of the input waveform. Okay. So as you're having a class, I will quickly get into the basics of full wave because I have to end over here. You're having a class. I think I have to manage some extra classes because it's not possible with the normal schedule. Otherwise, it's not possible to cover in just 4 classes whatever I had planned. It's a long syllabus and too many things got to be covered. Okay. Let me just finish off. Yeah.
Sir, you may take after 4 p.m. today.
Okay, not an issue. Whether it's possible.
No, sir. We have some practical classes, sir.
Take it on Sunday.
Yes, sir, we have practical classes.
Stop.
Generally continuous past 4.
Stop. Let us not get into too much of confusion. I will just talk about the basics of full wave. What I am talking about, we are getting into the basics of full wave.
हाँ भाई सर जो पढ़ा रहा है वो
You stop. You please mute your microphone. All of you mute your microphone kindly. Okay.
RF means
Sir,
So-
11 बजे से class है एक.
I told you mute your microphone. Don't talk at all. Now, when we are talking about this full wave rectifier, in the full wave rectifier, what are we having? We are having the same input information to be information which are having both the half cycles present or a bipolar input, and that is being fed to a transformer as being shown on your screen, which is being stepped down. Now here, when we are stepping it down, in what way are we stepping it down? That is the point of concern. Now here, the factor is this, that is the whatever information that we are having, it's being implemented according to the diagram in 2 different forms. One form is a center tap form, and in the other form, there is no center tap. I repeat my statement. In the first segment, right now I'm encircling on it, we are having a center tapping at the secondary winding of the corresponding transformer. But in the next form, which is given at the bottom, we are not having any such center tapping being present over there. So if we have these kind of implementations for 2 different implementations for full wave rectifier, what is the effective difference between the 2? When we take into account, let us say the second one, that is the bottom one, actually the bottom one is the one which we normally refer for full wave rectification, not the upper one, because of some disadvantages which we will be discussing later on. This bottom one is called to be a bridge rectifier, following because the diode combination, as you can check on your screen, follows a Wheatstone bridge combination. Okay, so it's basically a bridge rectifier. The complete circuit for the same is not properly being drawn in this context. The complete circuit for the bridge rectifier has been shown later on, because in this circuit, what has been not being shown is specifically the load. Load has not been shown. It has been kept open over here, but we have to connect a load and then realize the same, because the current has to flow through the load and realize the full wave rectified outcome. Okay, so that is the 2 different aspects. Now coming to the factor that is in bridge rectifier, what we have is there is no center tapping. So if you are not having any center tap, it means whatever secondary voltage we are observing at the secondary winding end is completely applicable to the Wheatstone bridge, like this, like the one has been shown. Let us say we are having a positive half cycle with this end plus and this end minus, and in the negative half cycle, this end plus and this end minus in the negative half cycle. And in that way, it will just repeat the idea, not repeat, it will have a same kind of idea corresponding to the secondary winding as we had for half wave rectifiers. But in the full wave rectifier counterpart, using center tapping principle as being shown on the top, what is the difference? Here we are having two diodes, D1 and D2. How conduction all takes place, that is the point of discussion that we'll take up later on. Okay. So in that case, what we're having a center tap at the middle of the corresponding transformer. Sorry, middle of the secondary winding. When we do so, what is the outcome? Outcome is this, that is, we are having, if it is at the middle, we are having a dual end outcome at the transformer, secondary winding of the transformer. Dual end outcome means what? It means plus minus for the upper part and plus minus for the lower part. Plus minus plus minus. So you are going to have a kind of a scenario in which you can definitely understand that if it is plus minus for one half cycle, it should be just the reverse for the other half cycle with minus plus representation because of the presence of the center tap. Once we do so, one of the diodes in one half cycle will conduct and the other diode will be off. This idea we will discuss in the next class. So that's all for today. So if you have any question regarding whatever we have discussed till now, you can raise your question or we will finish off the session today over here. We can't continue further because you're having a class. Any question from your end? I would like to say one thing, that is, please ask your questions from the next class onwards at the end of the session, not while the session goes on. Okay. I will give you 4 to 5 minutes at the end. I will keep 4 minutes at the end for discussion only. But if we continue with the so many discussions in between the session, it's very difficult to cover the course. Okay, within the stipulated time. So it will take an immense amount of time to finish off.
Excuse me, sir. Excuse me, sir. Sir, I am not included in the electronics class lab practical group.
Look, we have not started off with electronics class lab practical aspects. If when this ECS 5.1 will get started off, all of you will get intimated. Nothing to worry about it. It will happen in this platform
What
only.
is PO,
Okay,
sir?
sir.
ECS 5.1 will occur in MS Teams only. Okay.
Okay, sir.
Or in
sir,
Google Meet, depending on the faculty's choice.
Okay.
Okay.
Okay, sir.
Sir, what is PO? Power through resistance. Power given to the resistance or load.
PO. We have not gone through any kind of P.
Sir,
We have gone to PI.
PI, sir. PI.
Okay,
Input power.
Let me just do one thing. I take your attendance because we are having a class.
Sir, RF means, sir?
I have already mentioned number of times.
Resistance of
RF is the
power
power resistance of the diode. Power resistance. Just a minute. I have to take the attendance and then you can move. Download it. So attendance is downloaded. All of you can leave now.
Sir, what is PI? Power given to the resistance or load.
PI is the power given to the circuit and PDC is the power across the load. Okay.
Due to DC part.
The DC part across the load power, that is PDC, and PI is the input power to the corresponding half-wave rectifier circuit, according to the whatever expression that we have analyzed. Okay, based on that. So I have downloaded the attendance. All of you can leave. Okay.
Thank you.
That's all today. So I will talk with one of your CRs. I think one of your CRs can call me later on. We can fix up an extra class because it's not possible to finish off within the stipulated time without extra classes. Okay. That's all.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
आ गया मिस्टर दीपांशु राज, ग्रीटिंग्स ऑफ द डे। ग्रीटिंग यार अच्छा मैं यहाँ आया था एक्सपोजर के लिए बात करेगा कमेंट्स में लिखो सीड और मेरी व्लॉगिंग यूट्यूबिंग म्यूजिक करियर का क्या होगा? गाइस वो टाइम आ गया है शायद, आई डोंट नो, आई एम नॉट वेरी श्योर। इसका मुझे इंतजार नहीं था, बिल्कुल ही नहीं इंतजार था। ओके टेक्निकली ऐसे सिचुएशंस में लोग खुश होते हैं जब उन्हें उनकी जॉब की ऑफर लेटर आती है जो भी है, बट आई एम अभी अगर मैं ऑफर लेटर साइन करता इसका मतलब पता है तेरे को? इसका मतलब है यू आर साइनिंग अप फॉर द जॉब और तेरा बॉन्ड है, मतलब अगर तेरे को बॉन्ड ब्रेक करना है तो यू हैव टू पे समथिंग ना। हां आई एम सो हैप्पी टू सी कि एक और इंजीनियर अपने इस फील्ड से निकल के कुछ और करने के पीछे जा रहा है। ऑफर लेटर साइन नहीं करने वाला है ये तुमको क्यों लग रहा है? तेरे को क्यों लग रहा है तू साइन कर रहा है? बिग ब्रेन रणवीर बिग ब्रेन छोड़ रहा है नोवा। मैंने टी-शर्ट चेंज कर लिया क्योंकि मुझे लग रहा था कि वो टी-शर्ट थोड़ी अजीब सी है। एनीवेज तो दिस इज द टाइम व्हेन आई एम एक्चुअली गोना चेक द ऑफर लेटर जिसमें लिखा क्या होता है। इससे मुझे याद आया दिस वीक इज इन एसोसिएशन विद अन अकेडमी एंड अन अकेडमी हैज कम अप विद समथिंग रियली ग्रेट फॉर अन अकेडमी प्रोडिजी। ये टेस्ट 24th एंड 25th अप्रैल को होने वाला है। इसमें पार्टिसिपेट करके तुम 5 करोड़ रुपीस वर्थ के प्राइजेस जीत सकते हो, लाइक आईपैड, आईफोन, Amazon Echo एंड मेनी अदर थिंग्स। इसके अलावा जो टॉप रैंकर्स होंगे they will get a chance to virtually meet the players of Kolkata Knight Riders। जो क्वेश्चंस होंगे वो बेस्ट एजुकेटर्स के द्वारा क्रिएट किए गए हैं। तुम्हें तुम्हारा ऑल इंडिया रैंक मिलेगा और टेस्ट के बाद तुम्हें डिटेल्ड सॉल्यूशन मिलेगा। जो भी तुम्हारे डाउट्स होंगे तुम इजीली क्लियर कर सकते हो। चेक आउट द लिंक इन द डिस्क्रिप्शन, यूज द